Good morning, good evening. Thank you for joining us for the SPDK PMDK Intel Performance Analyzers Virtual Forum. My name is John Kariuki, and I'm a software engineer at Intel in the SPDK team. Performance benchmarking is one of the really cool things that my co-presenter Karol, Latecki, and I work on in the SPDK community. And that's because the SPDK community is all about designing for low latency and high throughput. And we get to be the first ones that performance benchmark new SPDK releases and highlight the outstanding efficiencies and performance that are enabled by running software that's designed for that next generation storage media, such as Intel Optane devices. In this talk, Karol and I are going to be sharing the performance benchmarking work we do. We're going to be talking about what we benchmark, why we benchmark, how we do it, and a few lessons that we have learned along the way. Here's what our agenda looks like. I'm going to start by setting the stage and talking about what we mean when we talk about I/O performance in the SPDK community. And then I'm going to talk about the performance benchmarking that we do on local storage. And then I'll punt it over to my co-presenter, Karol Latecki, who's going to talk about the benchmarking work we do to benchmark storage over Ethernet and virtualized storage. So first things first, let's talk about what we mean in the SPDK community when we talk about I/O performance. The first metric that you probably see us mention in the SPDK community when we're talking about performance is the IOPS per core. And we do this because SPDK components, they pull hardware from user space. And what we are measuring with this indicator is we're measuring how efficient the SPDK components are utilizing the available CPU resources to pull hardware from user space. Once we have a handle on the IOPS per core, the other metric that you hear us mention is the IO core scalability. So SPDK avoids all locks in the IO path. And with the IO core scalability metrics, what we are measuring is the scalability in the IOPS as we use more cores to perform IOs. As far as latency goes, polling has the effect of reducing the average latency and the latency variability. So we measure the average latency, and we also measure the tail latencies, the P90, P99, and 49s. For all three block storage usage models, right? The local block storage benchmarking and benchmarking block storage over Ethernet and virtualized block storage, we use 2 block sizes. For the small block workloads, we use a 4 KB block size, and we run 3 workloads. We run 100% random read workload, 100% random write workload, and a mixed workload that is 70% random read and 30% random writes. And then for the large block workloads, we use 3 workloads once again, and these are sequential. So we have a workload that's 100% sequential reads, a workload that's 100% sequential writes, and a workload that's a mix of 70% sequential reads and 30% sequential writes. We run these workloads after each SPDK release so that we can measure the performance of SPDK from one release to the next. And we publish performance reports on spdk.io. I have included the link to the performance reports in this presentation. If you follow this link and open one of the performance reports, what you're going to see is a very detailed report that has, like in this case, it looks like 38 pages with lots of details about our performance benchmarking effort. What we're doing here in a 45-minute talk is we're giving you an overview of what's in this report so that if you want to learn more, you can go find more information in these reports. So now let's look at the benchmarking work we do for local block storage. For local block storage, we have 4 test cases, and these test cases are designed to measure the efficiency, the scalability, and the latency of the SPDK NVMe block layer. The SPDK NVMe block layer uses the SPDK NVMe driver to submit and complete IOs to NVMe devices from user space. I'm going to talk a little bit about the difference between the SPDK NVMe driver and the BDEV. What the NVMe driver enables is it directly maps the PCIe bar for NVMe devices to a storage application's process space so that the application can submit IOs to the device as an NVMe submission queue entry and pull the completion queues for IO completions. If you don't want to deal with setting up queue pairs and submitting submission queue entries and polling for completion queue entries, then what you want to use in your application is the BDEV. The BDEV provides an abstraction that's created on top of these block devices, and that abstraction has common APIs for interfacing with different block storage devices. So from an application standpoint, the application uses an API to enumerate and claim block devices, and then it can perform asynchronous IO operations such as read and write to those devices. So the SPDK NVMe BDEV, it's very, very similar to what you see with the Linux kernel block layer, right? It has common operation for doing things like opening a block device, reading from a block device, or writing to a block device. When we do benchmarking on the local block storage, what we do is we configure the benchmark tool to use the SPDK NVMe BDEV and create a BDEV on top of each local PCIe attached NVMe device that we have in our test system. And then in the first test case, what we do is we use a small block workload at high queue depth, and we measure the maximum number of IOPS that we can get on a single CPU core. We also measure the maximum number of IO core that we can get on a single CPU core with the SPDK NVMe driver in this test case, so that we can show the overhead of using the NVMe BDEV instead of the NVMe driver directly. In the second test case, what we do is we increase the number of IO cores that are used by the benchmark, and then we measure the IOPS scalability as we increase the number of CPU cores that the benchmark is using. In the third test case, we measure the latency of these small block workloads at queue depth 1. And we do this for both the SPDK block layer and for the kernel block layer with both the libaio and IOUring engines. And then in the last test case, we limit both the SPDK and the kernel block layer to use just 4 CPU cores to perform IOs. And we measure the IOPS and latency as we increase the queue depth from queue depth 1 all the way to queue depth 128. All the scripts that we use to do local storage benchmarking are available in our GitHub repo under the test NVMe path directory. Now let's take a look at the SPDK NVMe BDEV IO efficiency. This slide here shows what we are measuring today on our test system, which has 24 NVMe SSDs And the workload we're using is the 4K random read. That's what we're using in this graph. And we're doing queue depth 128. And once again, all this is running on just one CPU core. We increase the number of SSDs from 1 all the way to 10. And what we see is, as we increase the number of SSDs, we see linear scaling in the IOPS that we get on a single CPU core up until 8 SSDs. And then we see a peak of 5.2 million IOPS with 10 SSDs on the test system that we're using today. Looking at the scalability of that lockless IO path of the SPDK NVMe BDEV. This is that test case 2, and what I'm showing here is the IOPS scalability for all 3 workloads, right? The 4K random read, 4K random write, and the 4K, the mixed workload, 70% 4K random read and 70% 4K random write. And what we see here, if we look at the first workload, which is the 4K random read workload, what we see is as we increase the number of IO cores that are available for the benchmark from 1 to 3, is we see linear scaling. And then we see a peak of about 10.9 million IOPS at 4 cores. And the reason this workload peaks at about 10.9 million IOPS is because that's the maximum we can do on this platform. This platform has PCIe switches, and they limit the performance of the NVMe SSDs that we have on this system. For the other 2 workloads, the random write workload and the mixed workload, the 70% random read and the 30% random write workload, we see linear scaling as we increase the IO cores from 1 all the way to 4. And then the performance peaks at 4 cores for the mixed workload and 5 cores for the random write workload. And that's limited by the storage. So now let's take a look at how we set up this benchmark for these high IOPS test cases. So in our test environment, we start with NVMe SSDs that are capable of high IOPS. And we're going to take a look at what those SSDs we're using are here in a couple of slides. And then we install them in a platform that's capable of many NVMe SSDs. In our system, we can have up to 24 NVMe SSDs. And then once we do that, we configure the benchmark tool to use the least number of CPU threads that we can use. And this is because with the SPDK NVMe BDEV, this is a poll mode implementation that uses each CPU core that the benchmark tool is configured to use. So if you give this benchmark tool a CPU core, it's going to utilize 100% of it. So since we're trying to measure the IO efficiency of the BDEV, to do that, we need to configure the tool to submit IOs to many SSDs from a single thread. And that's what I'm showing here in this configuration here that I have on the right, as I'm showing an FIO job that's configured to submit IOs to 6 NVMe SSDs, NVMe 0 and 1, all the way to NVMe 5 and 1. So this is the configuration we'd use to run the benchmark tool using just one IO core. When we scale the number of IO cores, so for instance, to scale the number of IO cores from 1 to 2, what we do is we add another section like this that I'm showing how up here, the job section. And that new job section is going to be submitting and completing IOs to the next 6 NVMe SSDs that we have in this system. So we are going to have another job, for example, file name 1, and that job is going to be configured to use SSDs NVMe 6 through 11. And then to do to submit IOs using 3 cores, we add another section for the next 6 SSDs that we have in the system, and so on until we've used all the SSDs. NUMA alignment is also important. So what we do with these FIO jobs is we also use the CPU allowed, like in the case of FIO, we use the CPU allowed field to configure these jobs to run on CPU cores that are on the same NUMA node as the NVMe SSDs that the job is using. The choice of the benchmarking tool, that's also important. That's what we've learned. FIO is the standard IO benchmarking tool out there in the industry, and it provides lots of flexibility. It's got lots of bells and whistles when it comes to how you define workloads. There's lots of great metrics. We in the SPDK community, we use FIO, right? And we even provide a plugin for the NVMe driver and the NVMe BDEV. But what we found out is all that flexibility comes at a cost. And for this use case, where we are benchmarking the performance of the SPDK NVMe BDEV when talking to locally PCIe attached NVMe devices, we have seen that there is a benefit to having SPDK tools like the NVMe path and the BDEV path that are highly optimized for IO completion and submission, and they have lower overhead when it comes to all this additional workload instrumentation type of overhead. What we measure when we use the SPDK tools versus FIO is we measure up to 2x more IOPS per core with the SPDK tools versus FIO. Next, we are going to look at the type of performance we see for that test case 4. So test case 4 is a test case where we take the SPDK NVMe block layer, the Linux kernel block layer with the libaio engine and the IO Uring engines, and we restrict the benchmark tool to only use for IO cores. And then we vary the Q depth from 1 all the way to 128. And as we're doing that, we measure the IOPS that we're getting on those 4 cores that we're using for IOs and the latency. So starting at Q depth 1, what you see is for all 3 block layers, right? For all 3 IO paths, right? The SPDK, NVMe BDEV, the Linux kernel block layer with libaio, and the Linux kernel block layer with IO Uring, is they started about the same numbers, right? Very close. They're very close numbers at Q depth 1. But as we increase the Q depth, by the time we get to about Q depth 4, Q depth 8, we start seeing the polling implementations pulling away from libaio. And then as we get to Q depth 16 and 32, SPDK pulls away from IO Uring. And what we're seeing at Q depth 64 is over 10 million IOPS with SPDK, and that is up to 2.9 times more IOPS per core versus IO Uring, or 5.8 more IOPS per core versus the libaio IO engine. Here is what our test system looks like. It's really just a standard Intel Xeon system with 2 CPUs, 384 gigabytes of RAM, and like I said earlier, we have 24 NVMe SSDs in it. Right now we're using the P4610 SSDs. So performance benchmarking takes a lot of time. It takes a lot of resources, and one of the things that we often have to contend with is, do we really have to benchmark every single release, right? Why do we have to benchmark every release? I mean, there are obvious changes where you need to do benchmarking. So for instance, when you have new hardware, right? If you get like new Gen 4 SSDs or CPUs, or you get new NICs, then yeah, it's clear that you need to do benchmarking in that case. If you go out and you optimize the software, then it's also clear that you need to do benchmarking. But what if you have a release that has a bunch of features that seemingly don't have any performance impact? Do you really need to do performance benchmarking? What we have learned in the SPDK community is, yes, we do need to always performance benchmark our releases. And we have seen some features that we did not anticipate to impact performance have negative performance impact. As an example, in the last LTS that we did, the 2101 LTS, there was a feature that was added to the NVMe driver to account for the protection information when calculating the maximum sector size. When that feature went in, we found out when we benchmarked the release that feature caused a 6% performance degradation to the NVMe driver. So when we benchmark these releases and we find these performance issues, we log them in GitHub, and then we do a Git bisect of the changes that went into a particular release and identify the root cause of performance degradation and address it. Thank you so much. I'm going to go ahead and pass it over to my co-presenter, Karol, who is going to talk about benchmarking network storage and virtualized storage.
Thank you, John, for the introduction. My name is Karol Latecki, and I work as a cloud software engineer. I've been working at Intel and SPDK project for the last 4 years. My responsibilities include doing performance measurements for SPDK, testing and validation, and managing the continuous integration system behind the project. Let's continue where John stopped and move to the section about block storage over Ethernet. Storage over Ethernet allows us to use various network fabrics to connect remote NVMe devices. In our tests, we use RDMA and TCP transport layers of NVMe over fabrics. We primarily focus on testing SPDK performance, but we also run tests using native Linux NVMF solution, which allows us to both compare its efficiency with SPDK and to check its interoperability as well. When testing storage over Ethernet, we run 4 test cases. First is the target IO core scalability. It is very similar to John has described in the local storage section. We run the initiator side with the fixed number of the CPU cores and scale the number of the target cores while running the IO workloads. This allows us to see how many IOPS and how much bandwidth do we gain with each added CPU core, and we continue to increase the number of cores until there's either no more gain or until we saturate the network link between the systems. The second test is the initiator core scalability test. It's very similar to the previous one. In this case, the target is the side where the number of the CPU cores is fixed, and we increase the number of CPUs on the initiator side. The third case is the latency test, where we typically use QDEP1 workloads. These are small block size 4K workloads between the target and a single initiator system. We run those tests using a single null block device so that there's no additional latency overhead from a hardware NVMe drive. Additionally, for this test case, we mix the Linux NVMF kernel and SPDK target and initiators, and this allows us to check their interoperability and does it have any performance impact on the test. And finally, in the fourth test, we check how the performance in terms of both IOPS bandwidth and latency changes with increasing number of connections done to the initiator side. Similarly to local storage tests, our automation scripts are available in SPDK code repository. Our test setup is made of 3 test systems, one acting as the target system and the other 2 as initiators. Each initiator is connected to the target system with a single 100 gigabit Ethernet link. The connection is back-to-back as we do not use switches in our setup. And having a high bandwidth network link like that is a must-have in storage over Ethernet tests, because a typical onboard network interface running at 1 or 10 gigabits per second would get saturated very quickly and become a bottleneck. The target system is the one hosting all the storage, so it is packed with multiple high-performant SSDs. In our case, that's 16 NVMEs, so that storage is not a bottleneck during the test. For the initiator systems, which are connecting to the target and doing all of the I/O requests, the most important resource on their side is a powerful CPU, preferably one with many CPU cores in case multiple I/O threads are needed. For the benchmarking tool that we have chosen for storage over Ethernet tests, we have picked the FIO, as it is, well, a standard universal tool for storage benchmarking. The other thing is that in storage over Ethernet, network plays an important factor. And one of the important metrics for network is the latency, and FIO has many great data provided for the latency buckets and average latencies. And as a final thing, John in the last section has mentioned SPDK performance tools such as BDEVPerf or NVMe perf, which have much less overhead than FIO. And while it is important in testing local storage, in case of testing storage Ethernet, it doesn't play that much critical factor, as FIO overhead is pretty small compared to the overall network overhead. All right, let's take a look at some example data. Let's take target I/O scaling as an example. I've picked TCP results data to present, as I feel that more people are interested in seeing TCP rather than RDMA. If you're interested in RDMA data, then this is also available on our performance report section on SPDK website, and the link is put in the first slides of the presentation, which was presented by John. As you can see in the chart, for 4K random read workloads, the performance scales nicely with addition of CPU cores up to 8 cores, which is more than enough to process 100 gigabits of traffic. And further adding additional CPU cores brings us very, very close to processing nearly 200 gigabits per second. As for the large block size sequential workloads, like in the case of 128K read workload, just a few cores will allow to saturate 200 gigabit network link. And in some cases, just one core is enough to do a bit over 100. In the previous section, John has mentioned testing new features and our own code changes, as two of the reasons why we do frequent performance reports. And I think this chart serves as a good example of that. The blue bars here represent SPDK 2001 release, while the orange bars show the results for 2004 release. And in 2004 release, we had a feature introduced called message zero copy, which, as you can see, allowed us on a single CPU core using sequential read workload. It allowed us to double our performance from about 50 to over 100 gigabits per second. As for comparing SPDK and kernel, in our tests, we compare those two solutions by using a metric in IOPS per core. And we observed that SPDK is up to 2 times better than its kernel counterpart with increasing number of connections. And now some of you may ask why SPDK has only 50% of the performance for the first result for the bar on the left. Just let me quickly inform you that the reason is that SPDK runs with a fixed number of CPU cores, whereas kernel solution can adapt its current CPU utilization to the current conditions. So it can decrease the utilization. Now, in the recent SPDK releases, we've introduced something called dynamic scheduler, which allows SPDK to do exactly that. So we expect to see this data point improved in the near future. For storage over Ethernet, we do some additional performance optimizations. One of them is already mentioned NUMA alignment that has visible influence on the results, as handling hardware placed on different sockets than the CPUs takes up additional CPU cycles. BIOS and OS settings, like power settings in BIOS or CPU governor settings in the OS, we typically always set them to the highest possible values. We also manually adjust the IRQ affinity settings to control which CPU cores are responsible for handling network interface interrupts. And for TCP layer, we do a number of additional sysctl changes, like increasing the number of send and write buffers for the packets, or increasing the size of backlog for incoming packets or incomplete packets. Okay, let's move to virtualized storage tests. So virtualized storage tests focus on utilizing SPDK and kernel vhost, which provides a local storage service as a process on a local machine to expose virtualized block devices to some other processes, like, for example, virtual machines. For those of you who are not familiar with vhost, there's a link at the bottom of this slide, which will take you to our documentation page where you can find more details. As for the test cases, we run a test for single core VM saturation. And what that means is we run a single core SPDK vhost process and increase the number of virtual machines attached to it and see how the performance behaves. We increase the number of virtual machines until the performance stops scaling or it drops. And we do that to know what is the maximum number of connected VMs so that we don't oversubscribe the vhost process. Next is the IO core scalability. Again, very similar to scalability tests in local storage and storage over Ethernet. we increase the number of vhost process cores along with the number of VMs and see how the performance scales along the way. Third test case is what we call a VM density test, where we run SPDK and kernel vhost with a limited number of CPU resources and attach a large number of VMs to it to see if vhost will be able to process desired levels of IOPS. Next, we have latency and IOPS test to see how these behave with increasing queue depth of the workload. And finally, as the last point, we have some additional performance options tests where we check various SPDK options to see how they affect the performance. Our test system is fitted with 24 NVMe drives, which is less than the maximum number of the virtual machines we run in the tests, which is either 36 or 72, depending on the test case. Because of that, the drives must be split into smaller parts so that all of the VMs can use them. We use vhost here for that purpose. And in the previous sections, we've talked about NVMe block devices in the SPDK. So what vhost does here is it attaches local NVMe SSDs to vhost process, creates NVMe block devices on top of them. Then additionally, in order to be quote unquote be able to partition them, creates logical volume block devices and exposes them using vhost controller to the virtual machine systems, either as a virtio SCSI devices or virtio block devices. Okay, let's see some data now. As I've just mentioned, we check SPDK vhost performance with various vhost stacks and BDEF combinations. This chart presents the result of testing the SCSI stack using NVMe BDEFs, that's the blue bars, and SCSI stack with logical volumes on top of the NVMe BDEFs, that's the green bars. This allows us to check what's the performance impact of additional layer, which the logical volumes are. The purple bars in the chart represent the block stack with logical volume block devices, and this allows us to compare SCSI and block stacks. As you can see, the scaling for all the test combinations is quite linear, and for the SCSI case, we're able to get to 2 million IOPS on just a single core. A couple of slides back, I've also mentioned a VM density test. For this test, we run the vhost process restricted with just 4 CPU cores and a number of VMs, each with SLA set for its IOPS at 10,000. And we run up to 72 of those virtual systems and attach them to the vhost process. For all the test cases, the SPDK stacks were able to meet the expectations, while with just 4 CPU cores, the kernel SCSI counterpart was not able to sustain the given SLA of 10,000 IOPS. And finally, for some additional tests during the virtualized storage section, we're also testing some additional features of SPDK, and this is one of them called LTO, link time optimization. It's a build feature of SPDK, so it has to be enabled prior to building the binaries. And as the name suggests, it does extra optimizations while building. For the SPDK vhost, it allowed us to increase the performance about 5% as compared to a default SPDK build. For the virtualized storage, again, the benchmark tool of choice is FIO for being a standard tool to benchmark the storage. We use it in the client server mode, which allows us to simultaneously run the traffic across all of the connected virtual systems. The automation scripts for testing virtualized storage, just as in the other two sections, are also publicly available in our repository. As for the test optimizations, the NUMA alignment requirement still stands. It's always important to keep in mind. Additional options include parameterizing FIO jobs to disable some of the metrics which are not needed, like latency measurements, to decrease the software overhead so that we can increase the overall IOPS results. Or especially for the VM density test, we manage the C groups in order to set SLA levels for the attached virtual machines. I would also like to briefly mention that we try to check our performance constantly. We do not only run performance tests on quarterly basis after each release, but we also use all the mentioned automation scripts in our continuous integration systems to run the performance tests every day in a loop, so that we have a constant flow of results, so that we can detect issues early and fix them as soon as possible. All right, that's everything from me. Thank you, everyone, and I'll hand it over back to John.
Thank you so much, Karol. And now let's take a look at some of the future plans that we have for our performance benchmarking effort in the SPDK community. The first thing that we're looking at is using the dynamic scheduler and reporting IOPS per watt metric. So today, all the benchmarking we do, we use the static scheduler. And what that means is our benchmark application or the applications we're benchmarking, they use 100% of the CPU cores that are assigned to them. In the SPDK 2101 release, the dynamic scheduler was added. And what the dynamic scheduler does is it moves threads around and adjusts CPU frequency and turns off idle CPU cores that are not being used. So it's designed for power savings and reduction in CPU utilization. If you want to learn more, Maciek has a demo later today where he'll be talking about the dynamic scheduler. The other capability we are looking to add to our benchmarking is benchmarking the NVMe of a VFIO user. And the next talk after this talk is actually going to be talking about VFIO user. So if you want to learn more about that, please listen into the next talk. We're also looking at benchmarking SPDK serving storage to containers. Monica has a talk later today where Monica has a demo later today where she will talk about the SPDK CSI that we use to serve SPDK storage to containers. And last but not least, we're looking at benchmarking some data services, right? We have a compressed BDEV and a crypto BDEV out there, and we're looking at adding that to our SPDK benchmarking. Thank you so much for listening into our talk, and we are now open for questions.